Okay, if you did not put 83 and 84 in Google Classroom, I need your hard copies with your name on them up here in the
Good morning, Dale
basket.
High School. It is Wednesday, February 22nd, 2023.
Okay, and our quiz is no calculator this morning, so I need your phones, smartwatches put up on the board, and your desk cleared off.
Teachers, part of this brief interruption. The students going on the 10th grade field trip to Crystal Bridges, please move to the bus loading zone at this time. That would be on the south side of our campus where our buses are always. Again, 10th graders going on the Crystal Bridges field trip, please go to the bus loading zone at this time. Thank you.
Let me get upstairs. Okay, what I was saying was this quiz does not have point values listed, but basically each question is a point. There's one question that asks you to make a table and to make a graph. The table's worth a point and the graph's worth a point. And then basically all the blanks, all the questions are 1 point each. This one, you can use a calculator, but I don't think it's helpful, so. But if you think you could use it, then feel free to. It says on there and it says up here.
Okay, anybody still working? Okay,
So we're moving on. So make sure that you have the two new handouts today, 86 and 87. 86 is the shorter one where we're going to talk about how you're supposed to know what a logarithmic graph looks like. And really I only have to give you one new piece of information, and then we need to connect a few things that we've done recently. And then the longer handout is also over logarithms, but it's kind of some of the properties you need to know, some of the question types like those that you'll see on the ACT, just kind of more of a mixed bag. Why do we need logarithms, things like that. So, of course, section 1.9 is good to know. That was when we did inverse functions. So if that was not important, we wouldn't spend class time on it. Same with exponential functions. If it wasn't important, we wouldn't spend a couple class periods on it. But just a fair warning, with logarithms start here in section 3.2, but then 3.3 will also be logarithms, and 3.4 will also be logarithms. So this one kind of snowballs a little bit more, and it is certainly one that you want to start off on a good footing. So, all right, so that starts right here. Okay, so really the only new piece of information that I don't think you may have heard in Algebra 2 to graph logarithmic functions is what I'm about to tell you in questions 1, 2, and 3. You need to understand this relationship between exponential functions that we just talked about and logarithmic functions that we're moving into. So log base 3 of x and 3 to the x, those two functions are inverses of each other. Likewise, log base 8 to the x and 8 to the x are inverses of each other. So we will ask you, and you need to know, what's the inverse of 5 to the x? Log base 5 to the x. And what's the inverse to log base 2 to the x? 2 to the x. So once you know that connection, you're going to see everything else I say on the rest of this handout is really just kind of fitting together some pieces of stuff that we've already talked about. So on this graph, what I really want to graph is this. Log base 2 of x plus 3. But before you're going to feel comfortable doing that, you've got to kind of step yourself through this process. So I would suggest that you first graph 2 to the x. So 2 to the 0, 2 to the first, 2 to the squared, 2 to the third, and he is exponential growth. And label him as 2 to the x. Now, for just a moment, you might say, why in the world are we graphing 2 to the x if we're really trying to graph log base 2 to the x plus 3? Well, 2 to the x is inverses with log base 2 to the x. And since we've recently talked about inverse functions, we know that just means you switch x and y. So 0, 1 becomes 1, 0, 1, 2 becomes 2, 1, 2, 4 becomes 4, 2, 3, 8 becomes 8, 3. You can connect as many points as you need to, but that is how you can discover what log base 2 to the x looks like. And all you have to do is know how to graph 2 to the x and know what it means to be an inverse function. Now, this is not important right now, but notice that there is this line of symmetry at y equals x that we had talked about. And then if you can graph that, the only other thing going on here is some of our transformation rules. Adding 3 directly to x is going to shift it left 3. So I can take all these points I was sure about, move them left 3 and replot them. And that is how you graph h of x. Now, just so you guys know, if you have more than one graph on your picture over here, you need to make sure you label which one you were actually asked to graph. So like you were asked to graph 2 to the x, don't just have 3 random graphs on here. Label one of them as 2 to the x or f of x, label one of them as g of x or log base 2 to the x, and label one of them as this stuff or h of x. Don't put multiple graphs on or multiple equations on one line and not say which one is which. Okay, we okay with that? Okay, so normally you're not being pushed in the right direction like the last three questions were. Normally it's just going to say, hey, figure out what this kind of graph looks like, and then maybe answer a few different characteristics about it. So even though it doesn't say to, when I look at this, I see there's a bunch of transformations happening to log base 3 of x, which I know is the inverse of 3 to the x. So me personally, I would quickly sketch 3 to the x, take a couple of those points, switch x and y, and I have log base 3 to the x. And unlike the last set, nobody really asked me to graph 3 to the x, so me personally, now that I'm done with it, I'm going to erase it and get it out of the way. I just don't want it to be in my way. But then when I look at this, there's really just 3 transformations happening. If I plug a number in for x, the first thing we're doing is adding 5 to x, so our first transformation should be shift left 5. So I'm going to move all of these points left 5. And now this represents log base 3 of x plus 5, which is closer to what I really want. Now I'm done with the one in red. Again, it was just kind of a stepping stone to help move me in the right direction. So you can either graph it very faintly or erase it, or just be super careful, but you got a lot going on here. The next transformation would be this negative, which reflects over the x-axis. So a point on the x-axis is still going to land on the x-axis. But otherwise, this now represents negative log base 3 of x plus 5. Now I no longer need the previous step, so I'm going to erase it and get it out of the way. And then to finish off, this -1 would be a transformation of down 1. So going to shift all the points down 1, reconnect them, and now I have a visual for I of x, which is what this one was called. So it's certainly not quick, and you can't reliably do it in one step. But again, if you understand these connections, graphing 3 to the x shouldn't be no problem. Switching the points, the x and y, to get new points shouldn't be a problem. Knowing that this is left 5 and moving all your points left 5, knowing that this flips it over the x-axis, so flip all your points over the x-axis. This shifts it down 1, so shift all your points down 1. It's a little tedious to have to do it in so many steps, but it is also a good, reliable way to figure out what we're supposed to be looking at. So again, when we started this handout, I said there's really all you needed to know. The only completely new thing was this relationship. Transformation rules we've been using, inverse functions we've been using. You just need to do it carefully, especially if you're putting multiple graphs on here, because it can get kind of convoluted there. But then once we have this in front of us, we can answer all kinds of stuff about it. I can see the domain approaches -5 on the left and infinity on the right. The x-intercept looks to be a little bit less than -4. Now once we know a little bit more about logarithms, we can solve for that to be an exact value, but right now we're just going to estimate it. And these graphs have a vertical asymptote. So the vertical lines are x equals. The vertical line that the graph approaches but doesn't cross. So x equals -5. But of course, all those characteristic questions depend on us looking at the correct graph. So we'll practice some more of that, but gives you an idea of how to proceed on those question types. Okay, any clarification questions y'all want to ask about this before we move on to the other one? Okay, then in our other handout, we need to look at some of the properties, look at a few of the trickier questions, review some of the stuff from Algebra 2. But a lot of this stuff is stuff that we're going to be using on a daily basis for the next several weeks. So first off, why are logarithms needed? Well, if I ask you a question like this one, I don't think you really need logarithms. What power of 2 gives us 4? 2. Because that's a nice even number, we can do that, fine. Don't do anything with logarithms. That would be more work. But over here, 2 to what power gives you 5? Because that's not a nice whole number, it's not something that we can quickly do. So we'll come back to this one once we do this, because it's the same thing. So we've got some tricks on how to solve, but this is why logarithmic functions are needed. If it's solving an exponential function, an exponential equation, and it's not one that we can do in our head, logarithms will tell us the answer to this, an exact answer. And since lots of things in nature occur naturally that way, especially science-related stuff, that's just going to be a skill that you guys need at some point. Okay, so to show you how to deal with that, and then also this is definitely something you saw in Algebra 2, but this is also big on the ACT. You need to know how to go from exponential form, which is these 4, to logarithmic form. Well, logarithmic form is going to have log in the answer. That's what makes it logarithmic form. And then the only thing you have to do to switch it from exponential form to logarithmic form is put log in your answer and then switch 2 of these things. So you just have to know which 2 to switch. So here it would be the 2 and the 9. So 3 squared equals 9 is the same thing as saying log base 3 of 9 equals 2. Switch to b and the c. Log base a of c equals b. Switch to 4 and the 2 and the 16. Log base 4 of 16 equals 2. And then sometimes when you do this, like this one, you switch the form and you just happen to stumble upon what x equals, which happens to be the solution. So the solution to this is, the exact solution is log base 2 of 5. Which is a little bit bigger than 2. I'll show you how to get a decimal out of that if you need a decimal. So sometimes just switching it from logarithmic form to exponential form is all that needs to be done to solve it. If it gets you down to x equals, then it solved it. Okay, do y'all remember switching the forms like this in Algebra 2? Okay. Well, if you feel comfortable with one direction, then you need to go the other direction as well, but you're just undoing it. So to get it out of logarithmic form, I don't want log to be in there. But in order for me to take that away, I need to switch these 2 around. Switch these 2 back. So the 2 that you were switching to put log out front would be the 2 that you need to switch back if you want it back in exponential. We okay with that? Okay, also with logarithms, when you look at your calculator, your calculator devotes 2 buttons to logarithms. It has a log button, and right below it, it has an LN button, which stands for natural log. So the fact that your calculator gives you 2 specific buttons, Cooper, you need to keep your phone put up. Gives you 2 specific buttons, gives you an idea of how important logarithms are. But notice, if I type this in, it does not let me change the base here. And when I type natural log, it doesn't ask me for the base either. That's because it's assumed that we know what those are. So natural log means log base e. The same e number that we saw in the compound interest formulas. So I'm not doing anything with these questions, I'm just rewriting them. This is the same thing as this. This is just a different way to look at this. And until you're comfortable with natural logs, sometimes you want to rewrite it so that you can see that e. What about if there's not a base written? Do y'all remember what that is? That is base 10. So same thing, until you feel like you know that frontwards and backwards, if there's not a base there, just squeeze in the number 10. So on your calculator, when you hit the log button, it assumes you want the common log, which is base 10. If you hit the natural log button, it assumes you want base e. Those are the 2 most common ones. Okay, so we will ask you to evaluate some logarithms without a calculator. So most of this really just boils down, if it's without a calculator, our answers are going to come out to pretty nice numbers most of the time. You just need to know how to read this. So I'm going to go the long way on the first one, just to kind of show you a connection to something else we've talked about, and then I'll show you how I really phrase it in my head and how quickly you can answer these things. So on this one, if I want to know what log base 7 of 7 is, well, you could set that equal to x. And so if I figure out what x is, I have my answer. Well, this is logarithmic form because it has a log in it. One thing you could do is you could switch it to exponential form, which we've talked about this morning. And just because we're more familiar with this is easier for our brains to keep up with what's going on. This is saying 7 to what power gives you 7? So the answer to that question is 1. Now, you don't really have to set it equal to x and switch the form just to phrase it that way. You can just do that in your head right here. There's no base written, so this is base 10. So this is really asking you 10 to what power gives you 100. Not 10 times what gives you 100, but 10 to what power gives you 100. This is saying 10 to what power gives you 10. This is saying 10 to what power gives you 1. What would the answer to that be? 0. Anything to the 0 power is 1. This is saying 3 to what power gives you 27? Answer is not 9. It's 3. Not multiplication. Even students that know this do that sometimes, especially if they're going too quickly. What about this one? What do you think the answer to this is? 1. Very good. If the natural log bugs you, you can just change it to say base e. This was saying e to what power gives you e. So that would be 1. This is not much different than this. E to what power gives you 1? 0. Anything to the 0 power gives you 1. And then of all of these, this one's probably the hardest. You got to use a little bit of exponent rules. So 2 to the first would be 2. But 2 to the negative 1, remember a negative exponent in the numerator is consistent with positive 2 in the denominator. So this equals negative 1. 2 to the negative 1 is the same as 1 over 2 to the positive 1. So I don't know if the ACT puts these type of questions on here, and I guess you could use your calculator on these, but we would certainly make these no calculator. As long as you know what it's asking you to do, most of these are pretty easy. Although I would maybe mark this one to look back at. That one's not easy for everybody. Okay, so when things don't come out to a nice whole number, like we saw on question 1, sometimes we want to be able to round it and see what the decimal is. Well, first off, before I tell you what the change of base formula is, what kind of answer do you expect this to be? This is not a nice whole number, but you should still be able to estimate. What answer would be too small? 10?
Oh, like 1.
Oh,
Okay, 1, because 3 to the first is only 3, and I need it to be 7, what number would be too big? 3 squared is 9, and I only need it to be 7. So I know my answer is somewhere between 1 and 2, which is good, but sometimes I might need that to be within like 3 decimals or 5 decimals. So there's a thing called a change of base formula, and this really first existed, as far as I know, because calculators don't ask you for the base. If you hit the log button, it doesn't let you say what the base you want it to be. If you hit the natural log button, it doesn't let you say what you want the base to be. Now, that's not so true anymore. Most of these calculators will let you type in the base, and I will show you that at some point, but you still need to know change of base for a couple reasons. One is, I think it still shows up on the ACT. 2, I know in college algebra they expect you to know what the change of base formula is. And 3, in calculus, there's a couple things we do, and to show you why they work, we do a proof with change of base. So change of base just says that if you have log base 3 of 7, that's the same thing as log base 10 of 7 over log base 10 of 3. And, or the natural log of 7 over the natural log of 3. We learn these two because these are the two ways our calculator can do, base 10 and base e. So I will type in both to show you it doesn't matter which one it is, but you do need to know both because sometimes we make it multiple choice. So if you just always do it one way, you're not going to know. But it was about 1.771. Okay, over here, I hope that you can see your answer is going to be a tiny bit more than 2 because 5 squared would be 25. But if you needed 3 decimals or 8 decimals in accuracy, you would either need to go to your calculator and ask it what's the log of 27 over the log of 5, or the natural log of 27 over the natural log of 5. That is considered the change of base formula. Whether you do base 10s or base e's, both of them work the same way. About 2.048. So I knew it was just a tiny bit more than 2, but I certainly couldn't get it that. I couldn't get it that accurate. So again, to be fair, this is getting kind of outdated because most calculators will let you type in a base of 5 or a base of 3 if you know where to do it. And I will show you that just in case it helps you on the ACT, but you still need to know change of base. And make sure you know both ways, base 10 or base E, in case it is multiple choice. And we only write it one way. Okay, next up is the property, the specific property that makes logarithms useful. If it was not for this property, logarithms would not be that useful, and we certainly wouldn't spend much of any time on these. But the main property of logarithms says that if you have an exponent on something that you're taking the log of, that exponent can come down out front. I didn't mean to duplicate these, but the reason that's important is if I ask you to solve this, tell me what value of x could you add 2 to it so that the exponent of it on 4 is the same thing as 6. First off, you can guess and check all day long. You're not going to guess what it is, at least not exactly. You might be able to get a decimal that's pretty close. But 2, it's this property that makes us be able to solve this. There's no other algebra property that you have that lets you solve for a variable that's stuck in the exponent. This is unique. So over time, this first step's not too important right now, but we could take the natural log of both sides. That's okay because I'm keeping it balanced. The reason why I know to do that is because now this x plus 2 is an exponent on something I'm taking the log of. So this property says, hey, that thing you're solving for, you can bring it down out of the exponent. Now, natural log of 4 and natural log of 6 are some weird decimal, but these are just numbers. So I could just distribute this. could undo adding a number by subtracting a number. And then I can undo times with divide. The answer to that, as I said, it'd be something you would never guess. But natural log of 6 minus 2 natural log of 4 all over the natural log of 4. Now at the end there, all I did was distribute, undo add, undo times. So this is pretty basic, even though it looks really complicated. You don't need to know why I took the natural log of both sides, but you need to see how this property was able to shine right here. Because of this property, I was able to take the thing I wanted to solve for out of the exponent and make it where I can use my previous skills to solve for it. Okay, and I'm going to go ahead and type this in. Okay, so that as a decimal would be about this. And just to convince you that even though this looks like an insane answer, and you might think that there's no chance that that could be correct, what we were trying to solve was 4 to the power of x plus 2 was supposed to be equal to what? So that value of x, as complicated as it looks, is the exact value that makes that equal 6. So don't let the messiness of the answer throw you off. But that is what makes logarithms important. The only way to get a variable out of the exponent like that. Okay, another property I need you to know, although this one you really only need to recognize the pattern. I will show you how it gets used in calculus so you know why we ask you to know this pattern. But this is one of the easiest ones to do, but then also students will miss it quite a bit because you don't really need to do much. You don't like have to struggle through it, so it's kind of hard to stick. But if you have a number whose exponent is log and the base is the same number of something, all of that is just going to simplify to the something. So maybe if we write a couple more examples. 3 to the log base 3 of 8 is just going to be 8. 5 to the log base 5 of 100 is just going to be 100. It's really easy to apply. I'd be happy to show you why it works that way when we get near the end of this unit. But that's pretty much the only way we'll ask you, and you might want to put that in your notes. There's a couple of examples. You might have a point or two on a quiz or a point or two on a test about that. And for years, I would just tell students that and tell you that you would use this in calculus. This actually came up for the first time this year in calculus yesterday. So they were actually trying to solve something like this, go from here to here. And so again, you won't be on the hook for this, but I still want you to write it down. I want you to see why we care about this property and why we expect you to know. So they're having to take something like the natural log of y equals this, and they needed to solve it for y equals. Well, first off, you can't just divide both sides by natural log, because this is not natural log times y, it's natural log of y. So we have this really fancy algebra trick that's called exponentiating, where we make the left side of the equation the exponent on e, and we make the right side of the equation the exponent on e. And that's balanced because I'm doing the same thing to both sides of the equation. And the reason why we do that is this guy, e to the log base e of y, just becomes y. It's using this property right here. And then the other side would be what y was equal to. So it's not hard to apply. And again, we're not going to make you exponentiate to solve. But I just wanted to give you some context to the property instead of just telling you that you need to know it. All right, we already looked at evaluating logarithms without a calculator earlier, but these questions are a little bit tougher because these, I think you need to apply some exponent rules. So if you know your exponent rules, then this is okay, but I think it's good for you to see a few examples. So on this question, I'm going to rewrite this. Instead of calling it 10 to the 5th in the denominator, I'm going to move it to the denominator or numerator and make it 10 to the negative fifth. That's weird for students because most of the time in math you want positive exponents, so you usually take a negative exponent, move it to the other side, and make it a positive exponent. For these questions though, it makes sense to move it up because now I can apply that property we just talked about. This is an exponent on something I'm taking the log of, so that can come down out front. There's no base written here, so if that bugs you, squeeze in a 10. And so your answer comes from -5 times this, and what is log base 10 of 10? So your answer is -5. So if you can think to rewrite it with the exponent rule, the rest of it is not too bad. So let's do that 3 more times to try to help that sink in. I could rewrite this as, instead of 1 over e to the 7th, I could write it as e to the -7th. Now this is an exponent on something I'm taking the log of, so this can come down out front. And you're left with -7 times 1, which is -7. If you have more than one term, make sure you make the whole thing negative. It's not just the x that becomes negative, but also the -1 that becomes negative. So move it up so that it fits the right format. Now this stuff is an exponent on something I'm taking the log of. The log of 10 would be 1, so that would be your answer. Move all of this up, but don't just make the 3x negative, the whole exponent becomes negative. Then you can bring this down because it's an exponent on something you're taking the log of. Natural log of e is still 1, so -3x minus 2 times 1 would be -3x minus 2. I think last year you probably did some expanding and condensing of logarithms, and we will do that as well. So when we do that, you will actually have an option on how to work these, but temporarily this is all you can do. Move them up, even if it makes a negative exponent, so that you can apply that property of bringing it down. Okay, so we're going to do a quick sketch of our logarithmic graphs. So with exponential functions, we graph 2 to the x and 3 to the x, and I told you 5 to the x and e to the x and 10 to the x all look the same. And then these are the inverses. So I think we may have done this exact one on your other handout, but log base 3 to the x is just the inverse of 3 to the x. Log base 5 to the x is the inverse of 5 to the x. But since 3 to the x basically looks like 5 to the x, their inverses basically look the same as well. So whether it's base 3, base 5, base e, base 10, they're all going to have the same domain. They're all going to have an x-intercept of 1. They all have a vertical asymptote at x equals 0. Now, they're not the exact same graph, of course. One of them is going to rise, some of them are going to rise a little bit quicker, some of them are going to hug this y-axis a little bit quicker, but just a general overview, they all basically look the same, just like exponential functions all basically look the same. Okay, and so we will ask you to find vertical asymptotes like we did on the other handout. So I guess if you have the graph, you can just look at it and see the vertical line, vertical is x equals, that it approaches but doesn't cross. So if you don't do any transformations, it should be at x equals 0. X equals 0, x equals 0, x equals 0. But if you shift your whole graph left 4, that's going to shift your vertical asymptote 4 as well. So I guess you can graph it if you want to, but if all you need is the vertical asymptote, it's going to be left 4 of where it was. Okay, these are the two that concern me though, because I don't think you've seen this before. Well, first off, if you only multiply the x by a negative, what kind of transformation is that? Reflect what? Good, y-axis. And if you flip these over the y-axis, I'm going to do this up here. If I flip them over the y-axis, the vertical asymptote is still here at x equals 0. That doesn't change where that is. So it's still at x equals 0, just based on the y-axis reflection. But the part that I think you may not have seen in Algebra 2, I'd love if you did, but generally you guys don't. What does adding 4 to x do? Moves it left 4 unless you're also reflecting by a negative, or reflecting over the y-axis. When you reflect over the y-axis, the transformation rules for left and right get reversed. And because that negative is not really just going to the x, it really goes to both. So this guy is actually reflected over the y-axis and then right 4, which puts the vertical asymptote there. This guy's flipped over the y-axis, and normally this would be left 7, but because I reflected it over the y-axis, the rules are switched, and he is actually going right 7. And I don't know that you've ever seen that before, but feel free to graph it in your calculator if you don't believe me, but those rules do switch when you flip over the y-axis. Just doesn't come up very much. All right, and then last piece for today. I don't have any specific homework for you guys, but I am going to ask that you spend just maybe 5 to 10 minutes reviewing this handout again before I see you next time. I don't see you on a weird schedule, so I don't see you again until next Monday, because this is a B week. So it would be beneficial if you look over some of this. But the last thing I need to show you is that, especially when dealing with logarithms, there's a good chance that you're going to come up with solutions that are considered extraneous. So extraneous solutions mean that our logic is good, our arithmetic's fine, everything we do works out great, but one or some of our answers just may not work. So for you to know if you have extraneous answers, you have to memorize this. It is not possible to take the log of a negative number or 0. The reason why you can't do that is because this would be like 3 to what power gives you 0? And there is no number. If we think about this graph, he is never 0. He's never 0, and he's also never a negative number. So you can't take the log of 0, and you can't take the log of anything negative. Now, that doesn't mean that your answer can't be negative. So looking at this one, so we're going to do lots of equation solving. We do some pretty basic ones in the first couple sections, but section 3.4, the last section we do with logarithms, is all about solving equations. But on this one, both sides have log base 3, so that's already balanced out. They both have log base 3, so we just need to make sure that the inside stuff is the same. So take away an x from both sides, take away a 5 from both sides. If this was a question on the quiz, some people would say this is extraneous because it's negative. Once again, it's okay to have a negative answer. You have to plug it back into the up here and make sure that you're not taking the log of a negative number or the log of 0. And if I plug -1 up there, I'm taking the log of a positive number, taking the log of a positive number, and I can see the left and the right are the same. So I even confirmed that that's correct. Negative answer is okay, log of negative number is not okay. So one more example so you can see one that is extraneous. Both the sides of this also have log base 3, so that part's already balanced. So we just need to make sure that the inside parts are balanced. This is a quadratic, so we would need to set it all on one side, set it equal to 0. Solve it, probably with factoring, although you could do quadratic formula if you wanted to. You get 2 answers, and if you circle that, then you're not set up to get full credit because one or both of these don't work. If you assume it's a negative number because it's negative, that's not necessarily true either. You actually have to plug them in up here and see what happens. If I plug in a 1, it does make the left and the right equal, but you can't take the log of a negative number. 1 is extraneous. It can, if you include it as part of your solution, it is not correct. Whereas if I plug in negative 3, 9 minus 3 would be 6. You can see the left and the right are equal, and I'm taking the log of a positive number, which is fine. So it's not that I made a mistake or anything, it just did not solve the original equation, so it didn't work. So over time, we have to reinforce that in our head. Never ever can we take the log of 0, never ever can we take the log of a negative number. Okay, so before you put this up, you might scan through it and see if there's any questions you want to circle or highlight or notes you want to give yourself. And again, please do yourself a favor and spend just a quick 5-10 minutes scanning over this between now and next Monday so that it's a little bit more familiar to you. But that's all I've got for you today. And you got about 12 minutes till you're dismissed.